Yeah, thanks a lot to the organizers for inviting me to give this talk. And so I work for a genetic testing company, and one of our big problems, similar to what Heidi said, is the high number of VOSs, especially like at Missense variants. And so improved computational predictions could really help immediately to increase the chances that our patients get like a positive diagnosis. So our goal here in this approach is just to boost the performance of the best available approaches to push the predictions to strong pathogenicity or benign evidence levels. And for this, we use a combination of ClinVar and our own in-house data. And with best tools, and I know it's subjective, I currently mean Revel and Alpha Missense. As you know, Alpha Missense applies deep learning to protein structure features, and Revel is a well-known meta predictor. And both, as you see in these histograms, assign consistently higher scores to pathogenic variants than to benign variants. And in the following, when I say pathogenic, I also include likely pathogenic. When I say benign, I also include likely benign. And as you see in the top right, the score distributions are actually pretty similar. And so we propose here to boost performance by first recalibrating the raw variant scores that come out of the tools separately for Alpha Missense and Revel in this case, and then to integrate them into a consensus. And for this, we use our in-house data as training set. Also for selecting genes where we have like a sufficient number of variants to enable such recalibration. And finally, we evaluate the consensus score on a holdout data set of variants from ClinVar. And why recalibrate? So when you look at gene-specific score distributions, you see that the distributions can be surprisingly different across genes. So here we see on the x-axis the Alpha Missense score, and on the y-axis the likelihood of finding a variant of the given pathogenicity at that score. And so now we're kind of supposed to apply like a global score cutoff to select pathogenic and benign variants, but obviously that would result in a lot of classification errors if the distributions are so different. On the other hand, in genes like SEMD9, the distributions overlap heavily between pathogenic and benign, so maybe we should trust predictions less there. And why integrate? So the scatter plot compares scores between alpha and Revel. So each pathogenic variant is displayed as a dot. The correlation is low, so the tools seem to pick up different signals, and since they are supposedly both doing a good job, integrating them might be a good idea. And how do we do this systematically? So first of all, I want to remove the gene bias that we've seen before. And therefore, I suggest to recalibrate and transform the raw scores into probabilities. That is the likelihood of a variant being pathogenic. And for this, we need to characterize each gene by two parameters: the fraction of known pathogenic variants and the AUC of how well benign and pathogenic variants are separated. Few parameters are good here because that makes the tools more robust and less prone to overfitting. And so AUC and fraction are sufficient to parameterize a calibration curve based on Fermi-Dirac statistics. I'll show on the next slide how to derive this curve. But here we first transform the scores into ranks, as you see on the right. Then use the curve to look up the probability of variants being pathogenic. So obviously, variants with the highest alpha scores get the lowest ranks and therefore the highest probability, which is shown in the red curve. Then you can also compare it to the sample probabilities, which is the black dots. And as you see, they match pretty well the theoretical curve. Finally, for each variant, we integrate probability is derived from alpha and Revel into a single joint probability in an overall method called Fidel. And here's a little bit about the details. So Fermi-Dirac models the thermodynamic equilibrium of particles across quantum states by maximizing their entropy. And we interpret this as a non-parametric estimate of the rank condition class probability. So briefly, equation 2 defines the calibration curve, translating ranks R into probabilities P. And the two unknowns, beta and mu, corresponding to Fermi-Dirac's temperature and potential. So we get these by solving a system of two equations. That is here on the top, equation 1 and 3, which we fit based on the number of pathogenic and benign variants and the AUC. So then for each variant k, we enter each method 1 to m. We plug the calculated probabilities into equation 4 to get the joint probability, which is like an ideal consensus across these tools. Then we replace the raw scores with these joint probabilities, and then can apply global thresholds, select pathogenic and benign variants, and assess the performance. So we assess performance based on the criteria that Heidi just showed us from ClinGen, and they define minimum requirements for computational tools to reach supporting moderate or strong evidence levels. Evidence is considered strong here at the very right end of the graph if predictions achieve a very high precision of 99%. And then obviously methods are better if they recall a higher proportion of benign or pathogenic variants at a fixed precision threshold. And we can now recall 80% of the pathogenic variants instead of 50% from alpha or Revel alone. That means we can assign strong evidence to 30% of the variants that have been too difficult to predict for each of the tools alone. We can push the approach even further by utilizing domains. Variability of scores can also be found across domains within the same gene. So this plot here on the bottom left shows the amino acid position of ankyrin D11 on the x-axis and the joint probability on the y-axis. And again, red dots are pathogenic variants and blue dots are benign variants. So even with the improvements that I described, in ankyrin D11, we would predict none of the known pathogenic variants with 99% precision. That is indicated by this red line. But it seems as if there are like two hotspots of pathogenicity that coincide well with the two well-known domains, the ankyrin repeat domain and the repression domain too. Domains we can also define from AlphaFold by the PAE plots. In many genes, such as this one, the domains match boundaries found in the literature pretty well. So we now just recalibrate each of the two identified domains and the remainder of the gene in turn. And this new joint probability allows us now to recover reliably 24 out of the 37 pathogenic variants that we couldn't predict before. So in summary, this gives us an ideal ensemble predictor that allows us to recall 80% of the pathogenic variants with less than 1% error. That's an improvement of 30% over alpha and Revel. And it also naturally suppresses bad predictions because then the calibrated probabilities would be close to 0.5 and in genes where the tools don't work well. And we can now predict variants leaning likely benign or likely pathogenic in the fraction 2 to 1 for about half of our in-house VOSs. The analysis of hotspots can further improve the recall. 5% maybe doesn't appear like much, but it can really help in the curation of difficult domains. Thank you very much. Generally, what I might want to add is these two steps also what you're facing in these kind of normalize. You need to normalize the data between different sources that you can integrate them. But I'm happy to answer any questions.
The performance that you showed, what was your test set? I couldn't make that out from the slides.
The test set was like a holdout data set from ClinVar. So variants that are not in our in-house data sets.
But certainly Revel probably was trained indirectly on a lot of those variants, right?
Yeah, that is true. So that might introduce a little bias. Yeah. So we should redo this with newer variants that were only published after Revel was finalized. Yeah.
Yes.